Hello everyone. This chapter will focus on technical principles of ZooKeeper. After this course, we'll be able to know concepts, system architecture, and some key features of ZooKeeper. First, let's take a look at the introduction to ZooKeeper. ZooKeeper is a distributed, highly available coordination service, which provides two functions. First is to prevent the system from single point of failures and provides reliable services for applications. And second is to provide distributed coordination services and manages configuration information. As an underlying component, ZooKeeper is used by upper layer components such as Kafka, HDFS, HBase, and Storm. Then let's take a look at the position of ZooKeeper Infusion inside. In Fusion inside Hadoop, ZooKeeper provides a centralized service for upper layer components. It exposes a simple set of primitives that distributed applications can build upon to implement higher-level services for synchronization, configuration maintenance, and groups and naming. Then let's take a look at the system architecture. A ZooKeeper cluster is a group of servers. Nodes in a ZooKeeper cluster have three roles: leader, follower, and observer. Generally, an odd number of ZooKeeper servers are configured. Only one node serves as the leader in a ZooKeeper cluster. The leader is elected by followers using the ZooKeeper Atomic Broadcast Protocol. It's used to receive and coordinate all write requests and synchronizes written information to followers and observers. When a client is connected to the ZooKeeper cluster and initiates a write request, the request is sent to the leader. Then, data changes on the leader node are synchronized to the followers in the cluster. The ZooKeeper Atomic Broadcast I've mentioned here is a user-defined protocol used by ZooKeeper to ensure the data or status consistency among nodes in the coordination system. Followers use this protocol to synchronize local ZooKeeper data to the leader and provide services based on local storage. As for follower, it has two functions. The first one is to prevent single point of failure. A new leader is elected from followers when the leader is faulty. And the second one is to process read requests and interact with the leader to process write requests. The observer does not take part in voting for election and write requests. It only processes read requests and forwards write requests to the leader, increasing system processing efficiency, and client is used for reading and writing data from or to the ZooKeeper cluster. For example, HBase can serve as a ZooKeeper client and use the arbitration function of the ZooKeeper cluster to control the active standby status of the H master. In a ZooKeeper cluster, how to decide which one is the leader? Well, an instance that wins more than half of votes during the election becomes the leader. The number of ZooKeeper servers in a cluster could be odd or even. For example, if it's odd, assume 2x plus 1, then the server needs more than x plus 1 votes to be a leader, and the disaster recovery capability is x. If it's even, assume 2x plus 2, then it needs more than x plus 2 votes to be a leader. Usually, you are advised to deploy ZooKeeper on an odd number of nodes. Then let me introduce some key features of ZooKeeper. While ZooKeeper is simple, ZooKeeper allows distributed processes to coordinate with each other through a shared hierarchical namespace, which is organized similarly to a standard file system. The namespace consists of data registers called znodes, and these are similar to files and directories. Unlike a typical file system, which is designed for storage, ZooKeeper data is kept in memory, which means ZooKeeper can achieve high throughput and low latency. The ZooKeeper implementation puts a premium on high performance, highly available, strictly ordered access. The performance aspects of ZooKeeper means it can be used in large, distributed systems. The reliability aspect keeps it from being a single point of failure. The strict ordering means that sophisticated synchronization primitives can be implemented at the client, and it is replicated, like the distributed process it coordinates. ZooKeeper itself is intended to be replicated over a set of hosts called an ensemble. The servers that make up the ZooKeeper service must all know about each other. They maintain an in-memory image of state, along with the transaction logs and the snapshots in a persistent store. As long as a majority of the servers are available, the ZooKeeper service will be available. Clients connect to a single ZooKeeper server. The client maintains a TCP connection through which it sends requests, gets responses, gets watch events, and sends heartbeats. If the TCP connection to the server breaks, the client will connect to a different server. Besides, ZooKeeper is ordered. ZooKeeper stamps each update with a number that reflects the order of all ZooKeeper transactions. Subsequent operations can use the order to implement higher-level abstractions, such as synchronization primitives. Based on the ZooKeeper consistency, all servers connected to a client are displayed in the same view, so the read operations can be performed between the client and any service. For writing process, this figure shows the process of ZooKeeper processing the write request. At first, the client initiates a write request to any server. Then the server sends this request to the leader. After receiving the write request, the leader sends the write request to all nodes and confirms whether the write operation can be performed. The followers send ACK messages. The leader determines whether the write operation can be performed based on the ACK messages. If the number of write operations that can be performed is greater than 50% of the total instances, the write operation can be performed. After that, the leader sends the result to the followers and performs the write operation. Then the leader data is synchronized to the followers. The whole write operation is complete. ZooKeeper uses ACLs to control access to its znodes, which refers to the data nodes of a ZooKeeper data tree. The ACL implementation is quite similar to Unix file access permissions. It employs permission bits to allow or disallow various operations against a node and the scope to which the bits apply. Unlike standard Unix permissions, a ZooKeeper node is not limited by the three standard scopes for user, group, and world. ZooKeeper does not have a notion of an owner of a znode. Instead, An ACL specifies sets of IDs and permissions that are associated with those IDs. IDs are specified using the form scheme ID, where scheme is the authentication scheme that the ID corresponds to. ZooKeeper has the following built-in schemes. World has a single ID, anyone that represents anyone. Auth doesn't use any ID, represents any authenticated user. Digest uses a username password string to generate MD5 hash, which is then used as an ACL ID identity. Authentication is done by sending the username password in clear text. When used in the ACL, the expression will be the username base 64 encoded SHA-1 password digest. IP uses the client host IP as an ACL ID identity. The ACL expression is of the form ADDR/bits, where the most significant bits of ADDR are matched against the most significant bits of the client host IP. In addition, ZooKeeper supports the following permissions. For create, you can create a child node. For read, you can get data from a node and list its children. For write, you can set data for a node. For delete, you can delete a child node. For admin, you can set permissions. The create and delete permissions have been broken out of the write permission for finer grade access controls. In security mode, ephemeral nodes will be deleted after sessions are expired. Therefore, such information is added to the audit log, helping understand ephemeral node status. Username needs to be added in audit log for all the ZooKeeper client operations. Here shows some basic commands for ZooKeeper client about how to invoke a ZooKeeper client, or create a node, or create node data. Just take a quick look. These are easy to understand. Then let's take a look at the relationship between ZooKeeper and other components. For streaming, while ZooKeeper selects the active nimbus of streaming, to be more specific, it provides the following functions. Many nimbus processes attempt to write nodes to ZooKeeper. However, only one nimbus process can create the node successfully. The nimbus process that succeeds becomes the active one, and the standby nimbus processes are listening to the ZooKeeper node. After the active nimbus process fails, the node is removed. Then, standby nimbus processes receive the message. As the client of a ZooKeeper cluster, ZK failover controller monitors the state information of name node. The ZKFC process is deployed in both the active node and standby node of HDFS name node. The ZKFC of HDFS name node connects to ZooKeeper and saves information such as host names to ZooKeeper. Under the znode directory, let's say /Hadoop, name node that creates the znode first is considered as the active node, and the other is the standby node. HDFS name node standby watches the active name node information through the ZooKeeper watcher. When the process of the active node is ended abnormally, the HDFS name node standby detects that some changes occur in the /Hadoop znode directory using ZooKeeper, and then name node performs the active or standby switchover. Resource Manager tries to write the election information into ZooKeeper when the system starts. The resource manager, which writes the information into ZooKeeper successfully, first is elected as the active resource manager. The other one is elected as the standby resource manager. The standby resource manager monitors the election information of the active resource manager through ZooKeeper at regular time. The active resource manager creates a state store directory in ZooKeeper to store application information, and the standby resource manager obtains application information from the state store directory and restores the data when the active resource manager is faulty. Each region server registers itself to ZooKeeper ephemeral node. ZooKeeper stores the HBase information, including the HBase metadata and HBase address. HMaster detects the health status of each H-region server using ZooKeeper and monitors them. And HBase can deploy multiple HMasters, like HDFS name node. When the active HMaster node is faulty, the standby HMaster node obtains the state information of the entire cluster using ZooKeeper, which means that HBase single point of failures can be avoided using ZooKeeper. So this chapter mainly talks about ZooKeeper, including its functions and position in Fusion Insight, service architecture and data models, read and write progresses as well as consistency, creating and permission setting of ZooKeeper nodes, and also relationship with other components. Okay, that's all for ZooKeeper. Thank you.